What do we really know about aliens? It's a question that's intrigued humanity for centuries, but the answer has always felt just out of reach. We've imagined them in countless ways, from little green figures with big eyes to advanced civilizations far beyond our understanding. But what if the clues have been right in front of us all along? Over the years, we've made discoveries, small hints, strange signals, and unexplained phenomena that make us wonder, are we really alone in this vast universe? From mysterious radio pulses in the night sky to unexpected findings on Mars, there's more to the story than most people know. Each piece of evidence brings us one step closer to uncovering the truth about what or who might be out there. In this journey, we'll explore these alien facts, facts that have puzzled scientists, sparked debates, and fueled imaginations. Some of them might surprise you. Others will leave you thinking about the endless possibilities the universe holds. And either way, you're about to learn the facts like we know to be true about aliens. And without further ado, let's rewind to 1976, where we found chemical signatures of life. In 1976, NASA's Viking program made history by landing 2 spacecraft on the surface of Mars, marking humanity's first attempt to conduct experiments on Martian soil. The Viking landers were designed to study the red planet in detail, and a crucial part of their mission was to search for life. But what they found, or didn't find, has been the subject of heated debate for decades. One experiment conducted on board the Viking landers hinted at something extraordinary, the possibility of life on Mars. The experiment, known as the Labeled Release Experiment, was designed to detect biological activity in Martian soil. It was simple, but revolutionary. The Viking landers collected samples of Martian soil, which were then mixed with a nutrient solution containing carbon molecules labeled with radioactive carbon-14. If microorganisms were present in the soil, the theory went, they would metabolize the nutrients and release gases, specifically radioactive methane. And that's exactly what happened. When the soil sample was mixed with the nutrient solution, the sensors on the Viking landers detected the release of radioactive methane gas. This suggested that something in the soil was metabolizing the nutrients, a potential sign of life. It was a finding that left scientists both excited and puzzled. Could it be that Mars, the barren, cold desert planet we had always assumed was lifeless, was home to microorganisms? But as with many discoveries in science, things weren't that simple. While the Labeled Release Experiment produced a positive result, other experiments on the Viking landers failed to detect any organic molecules in the soil, organic molecules being the building blocks of life. Without the presence of these molecules, NASA scientists declared the methane production a false positive, concluding that some unknown chemical reaction, not biological activity, was responsible for the results. Yet, not everyone agreed with that conclusion. Gilbert Levine, the scientist who designed the Labeled Release Experiment, has long maintained that the results pointed to life. In fact, he has spent much of his career advocating for a re-examination of the data. Levine's argument is simple. The other experiments on board the Viking landers were not sensitive enough to detect the kind of faint organic signatures that might exist on Mars. In other words, just because those experiments didn't find organic molecules doesn't mean they weren't there. And Levine isn't alone. In the years since 1976, Other scientists have reanalyzed the Viking data and have come to similar conclusions. They argue that the soil on Mars contains compounds, like perchlorates, that could have destroyed any organic molecules during the experiments, leading to the negative results. If that's the case, the Viking landers might have detected life on Mars after all, and we simply weren't equipped to recognize it at the time. It's a tantalizing possibility, and one that has kept the debate about life on Mars alive for nearly half a century. But even more intriguing is what this discovery could mean in the broader context of our search for extraterrestrial life. If microorganisms could exist on Mars, surviving in its cold, dry, and irradiated environment, what other forms of life might be hiding in the more hospitable regions of our solar system? Mars, after all, is just one planet. There are moons in our solar system like Europa and Enceladus that have subsurface oceans where liquid water and volcanic activity might create environments capable of supporting life. If microbial life can survive on Mars, then these other celestial bodies, with their oceans and energy sources, might be teeming with alien life forms. The Viking landers' discovery, or near discovery, has fueled a shift in how we approach the search for life beyond Earth. But the Viking experiments did more than just spark scientific debate. They laid the groundwork for future missions to Mars. Since 1976, we've sent more advanced rovers, orbiters, and landers to the Red Planet, each equipped with more sophisticated tools for detecting signs of life. NASA's Curiosity and Perseverance rovers, for example, have found organic molecules in Martian rocks, bolstering the idea that Mars once had conditions suitable for life. These findings, coupled with the discovery of seasonal methane spikes in Mars's atmosphere, have made scientists rethink the Viking results and reconsider the possibility that Mars might still harbor life, even if only in microbial form. The Viking landers taught us a valuable lesson. The search for life isn't easy, and sometimes the answers aren't clear-cut. But the fact that we even found chemical signatures suggestive of life on Mars was groundbreaking. It showed us that the possibility of extraterrestrial life isn't just science fiction. It's a real, tangible question that we are capable of answering with the right tools and persistence. As we continue our exploration of Mars, one thing is clear. The Viking landers' experiments opened the door to a new era of planetary science, one where the question of life beyond Earth is no longer just speculation. We now have more advanced technology, more data, and more understanding of the Martian environment than ever before. And while we may not have definitive proof of life on Mars yet, the Viking mission showed us that the evidence might be closer than we think. In the end, the Viking landers' discovery, or near discovery, of life on Mars remains one of the most intriguing alien facts we know today. It's a reminder that the universe is full of surprises, and that the search for life is a journey filled with unexpected twists and turns. The Viking landers may not have given us the definitive answer to whether or not we're alone in the universe, but they brought us one step closer to understanding the mysteries of life beyond Earth. So, as we look back on this pivotal moment in the history of space exploration, we are left with more questions than answers. But that's what makes the search for alien life so fascinating. The truth is out there. It's just waiting to be discovered. Just a year after the Viking landers made their intriguing discovery on Mars, another event took place. one that would remain one of the most tantalizing alien-related mysteries in modern history. In August 1977, a radio signal was detected from deep space by Ohio State University's Big Ear Radio Telescope. This wasn't just any signal. It was a brief but powerful burst that was so unusual, so unexpected, that the astronomer who saw the data scrawled a single word in the margins of the printout: "Wow." And just like that, the WOW signal became a legendary moment in the search for extraterrestrial life. But what exactly was the WOW signal? The signal was detected in a part of the radio spectrum, 1420 MHz, reserved for astronomical research. This frequency is important because it's associated with hydrogen, the most abundant element in the universe. Any civilization capable of interstellar communication would likely understand the significance of this frequency, making it a logical choice for sending out a message to the stars. So, when this strange 37-second signal appeared out of nowhere, astronomers immediately took notice. There was something especially curious about the WOW signal. It didn't seem to come from anywhere familiar. The signal's origin was traced to a location near the constellation Sagittarius, but there were no known stars or planets in the area that could explain it. To add to the mystery, natural sources of radio waves like pulsars or quasars typically span a broader range of frequencies, but this signal was confined to a narrow band. It didn't match the signature of any known celestial phenomenon. That left only a few possibilities. It was either a natural event we didn't yet understand, or it was the work of something or someone intelligent. The sheer strength of the signal was another puzzle. If the signal had indeed come from deep space, it would have required an enormous amount of energy to travel across light years and still be detectable by Earth's telescopes. Whatever sent it had to have access to technology far more advanced than anything we have today. Could this have been the first direct evidence of an alien civilization trying to make contact? Some scientists thought so. However, despite its importance, the WOW signal has never been detected again. For years after that fateful night, astronomers pointed their telescopes back to the same region of space, hoping to catch another glimpse of the mysterious transmission. But the sky remained silent. The signal's fleeting appearance has only added to its enigma. Was it a one-time message from an alien civilization that has since gone quiet? Or was it some rare cosmic event that we happened to catch by pure luck? One possible explanation that some researchers have proposed is that the signal was caused by a comet passing through the region. Comets can release large amounts of hydrogen as they travel through space, and this hydrogen could theoretically produce a signal in the 1420 MHz range. However, this theory remains speculative, and many in the scientific community are skeptical. After all, no comet has ever been shown to produce a signal quite like the WOW transmission. Another theory is that the signal was a case of interference from a satellite or some other man-made source. But this explanation doesn't quite fit either. The 1420 MHz frequency is internationally protected, meaning that Earth-based transmissions in this range are strictly regulated. In other words, it's highly unlikely that the signal originated from Earth. If it wasn't man-made and it didn't have a natural origin, then what could it have been? The WOW signal has remained a subject of fascination for both scientists and the public alike. Its implications are profound. If the signal truly was a message from another civilization, it would be the first piece of evidence that we are not alone in the universe. But without a repeat signal, there is little more we can do than speculate. The search for extraterrestrial intelligence, SETI, has since expanded, with astronomers using increasingly sophisticated tools to scan the cosmos for more signs of alien life. Radio telescopes around the world continue to monitor the skies, listening for anything that might resemble the WOW signal. While we have yet to detect another signal of its kind, the WOW moment has driven the field of SETI forward, keeping alive the hope that one day we might make contact. Perhaps what makes the WOW signal so compelling is that it encapsulates the mystery of the search for alien life. It was brief, unrepeatable, and left us with more questions than answers. In many ways, it's a perfect metaphor for the ongoing quest to find out whether we are alone in the universe. We get these fleeting glimpses, whether it's methane on Mars, strange objects in space, or unexplained radio bursts, but the definitive proof always seems just out of reach. Even though we may never know for certain what caused the WOW signal, its legacy endures. It serves as a reminder that the universe is vast, and there is still so much we don't understand. Whether it was an alien transmission or a rare cosmic phenomenon, it opened our eyes to the possibilities that lie beyond our world. And as technology advances, who knows what other signals we might discover hiding in the background noise of the cosmos. For now, the WOW signal remains one of the most fascinating unsolved mysteries in the search for extraterrestrial life. It may not have given us all the answers, but it's a powerful reminder that the truth is out there, waiting to be discovered. And so, the search continues. Our ears remain attuned to the stars, hoping that one day we might hear that signal again. Fast forward to 1996, when NASA made an announcement that sent shockwaves through both the scientific community and the general public. Scientists claim to have found what appeared to be fossilized evidence of microbial life in a Martian meteorite, ALH84001, that had been discovered in Antarctica more than a decade earlier. The idea that ancient life might have existed on Mars reignited the age-old question: are we truly alone? This potato-shaped meteorite, blasted off the surface of Mars millions of years ago, wandered through the solar system until it eventually crash-landed in Antarctica, where it was discovered in 1984. Though it looked unremarkable at first, closer examination of its structure and composition revealed some astonishing details. The meteorite was thought to have formed on Mars around 4 billion years ago, during a time when liquid water might have existed on the Martian surface, a key ingredient for life as we know it. But it wasn't just the age or origin of the rock that got people talking. When scientists at NASA studied ALH84001 under a microscope, they found several intriguing features that resembled signs of life. First, they discovered organic molecules, complex carbon compounds that are often associated with biological processes on Earth. The presence of these molecules suggested that, at some point, conditions on Mars could have supported life. Perhaps even more compelling were the tiny structures found within the rock. Tiny, worm-like shapes that some researchers interpreted as fossilized nanobacteria. These structures were much smaller than any known bacteria on Earth, which made them difficult to classify. But their similarity to bacteria found in extreme environments on our planet gave scientists reason to believe that they could be remnants of ancient Martian life. To add to the excitement, scientists also detected magnetite crystals in the meteorite, which are sometimes produced by bacteria here on Earth. For a moment, it seemed like we had found the first direct evidence of extraterrestrial life. The discovery made headlines around the world, capturing the imagination of millions. The idea that life could have existed on Mars and that we might be holding physical evidence of it in our hands was nothing short of revolutionary. But, as with many bold claims, this one came with controversy. While NASA's initial findings were met with excitement, skepticism soon followed. Critics argued that the organic molecules found in ALH 84001 could have been the result of contamination from Earth rather than evidence of Martian life. After all, the meteorite had spent millions of years drifting through space and had been exposed to various elements after landing on Earth. Could it be that the supposed signs of life were actually just the result of earthly contamination? The debate didn't stop there. Many scientists also questioned the interpretation of the tiny, worm-like structures found in the meteorite. While some believed they were fossilized bacteria, others suggested that these formations could have been created by non-biological processes, perhaps the result of chemical reactions or the meteorite's exposure to high temperatures and pressures during its journey from Mars. As for the magnetite crystals, further studies showed that they could also be formed through non-biological means, weakening the case for life. Despite the criticisms, some researchers have continued to stand by the original findings. They argue that the evidence of organic molecules and magnetite, combined with the discovery of the nanobacteria-like structures, is too compelling to dismiss outright. While the scientific community remains divided, one thing is clear. ALH 84001 opened up new possibilities in our search for life beyond Earth. But what does this meteorite really tell us about Mars? For one, it suggests that Mars may have had the right conditions for life billions of years ago. During that time, the planet's surface was likely much warmer and wetter than it is today, with rivers, lakes, and even oceans that could have provided a habitat for microbial life. If life did exist on Mars during this period, it might have left behind traces that we can still detect today, whether in the form of fossils, like those found in ALH 84001, or through the presence of organic molecules in the Martian soil. The discovery of ALH 84001 also raised an important question. If life once existed on Mars, could it still exist today? While Mars is now a cold, barren desert, it's possible that microbial life could survive beneath the surface, protected from the harsh environment. Recent missions to Mars, such as NASA's Perseverance rover, are specifically designed to search for signs of ancient life and to collect samples that could be returned to Earth for further study. These missions are a direct result of the questions raised by the discovery of ALH 84001. In the years since the initial announcement, new technology and scientific advances have allowed us to study Martian meteorites in greater detail. We've learned more about Mars' geological history, and we've discovered that organic molecules, similar to those found in ALH 84001, are present in Martian rocks and soil. These findings don't necessarily prove that life once existed on Mars, but they do suggest that the planet may have been more hospitable to life in the past than we once thought. The story of ALH 84001 is a reminder that the search for life beyond Earth is a slow, methodical process. Each discovery brings us closer to answering one of humanity's oldest questions, but it also raises new questions and challenges. Was the evidence found in this meteorite truly the remnants of Martian life, or was it a case of mistaken identity? We may never know for sure, but one thing is certain. The discovery of ALH 84001 has changed the way we think about Mars and the possibility of life elsewhere in the universe. As our technology improves and our understanding of Mars deepens, we may one day find definitive proof of life beyond Earth. Whether it's through meteorites like ALH 84001 or direct exploration of Mars, the evidence we need is out there, waiting to be uncovered. In 1961, radio astronomer Frank Drake introduced the world to a groundbreaking way of thinking about alien civilizations, the Drake equation. It was a simple but profound formula designed to estimate the number of advanced extraterrestrial civilizations in our galaxy capable of communicating with us. By multiplying a series of probabilities, from the rate of star formation to the fraction of planets that might develop intelligent life, Drake's equation aimed to give us a clearer picture of just how many other civilizations might be out there. At the time, many of the numbers used in the equation were little more than educated guesses. We knew relatively little about the number of planets in the galaxy, let alone how many of them might be suitable for life. Drake himself estimated that there might be around 10,000 communicating civilizations in the Milky Way. While this number seemed optimistic, it was just that, a hypothesis based on the limited knowledge available at the time. Fast forward to 2001, and a new group of researchers decided to revisit the Drake equation using more advanced data and refined estimates. By then, we had learned a lot more about the galaxy and the types of planets it holds. Thanks to missions like Kepler, we now had a clearer sense of how many stars host Earth-like planets and how many of those planets might lie in the so-called habitable zone, where liquid water could exist. This new data led to an even more startling conclusion. There could be hundreds of thousands of life-bearing planets in our galaxy alone. This new estimate didn't just build on Drake's original work, it expanded the scope of what we believed was possible. For the first time, we had real numbers to back up the idea that life might be common in the universe rather than a rare phenomenon. Researchers calculated that habitable planets could be as little as a few hundred light-years away, a distance that, while vast, is far more manageable in the grand scale of the cosmos. The habitable zone concept was key to these calculations. Also known as the Goldilocks zone, it refers to the area around a star where conditions are just right for life, not too hot, not too cold. In this zone, water, a crucial ingredient for life as we know it, can remain in liquid form. Many of the exoplanets discovered in recent years lie within this zone, suggesting that conditions similar to those on Earth may not be as unique as we once thought. But the Drake equation doesn't just stop at habitable planets. It also factors in the likelihood that life, once it develops, becomes intelligent and, even more critically, capable of interstellar communication. This is where things get even more interesting. Life on Earth has existed for billions of years, yet humans have only had the technology to send and receive messages across the stars for a little over a century. So even if intelligent life exists on many planets, the window during which we might be able to communicate with them could be relatively short. The researchers in 2001 didn't just focus on life as we know it. They also considered the possibility of more advanced, technologically superior civilizations. Some scientists have speculated that intelligent life might not even dwell on planets at all, but in massive structures like Dyson spheres that harness the energy of entire stars. The Drake equation, updated with modern data, opened the door to these more speculative ideas about alien life. As with any model, there's still a lot of uncertainty. Many of the numbers in the equation are estimates, and each comes with its own range of possibilities. For instance, we don't know exactly how likely it is that life will develop on any given planet, let alone become intelligent. And we certainly don't know how long intelligent civilizations might last, especially given our own precarious situation here on Earth. But even with these uncertainties, the updated Drake equation paints a picture of a galaxy that might be teeming with life. If these calculations are accurate, it means that the search for extraterrestrial life isn't just a wild goose chase. It suggests that life might not only exist on distant worlds, but might be much closer than we ever imagined. And if life exists in such abundance, then the next question becomes, why haven't we made contact yet? This is where another theory, known as the Great Filter, comes into play. The Great Filter hypothesis suggests that while life may be common, intelligent civilizations capable of interstellar communication might be rare or even non-existent, because most civilizations don't survive long enough to reach that stage. Whether it's because of natural disasters, self-destruction, or some other cosmic roadblock, civilizations may be wiped out before they ever get the chance to send a message across the stars. The 2001 recalculations of the Drake equation didn't just reignite hope that we might one day find life beyond Earth. It also added a new layer of complexity to the search. The more we learn, the more we realize just how delicate and unique intelligent life might be. Still, the numbers are encouraging. The galaxy could be filled with habitable worlds, each with its own potential for life. Today, we're better equipped than ever to search for that life. Missions like the James Webb Space Telescope, launched in 2021, have the capability to analyze the atmospheres of distant exoplanets for signs of biosignatures, gases like oxygen and methane that could indicate the presence of life. In fact, some researchers believe that it's only a matter of time before we find concrete evidence of alien life, whether it's microbial organisms or something far more advanced. The updated Drake equation has given us a roadmap showing that the odds might be in our favor. And while the search is far from over, it's clearer than ever that life, perhaps even intelligent life, could be lurking just beyond the reach of our telescopes. In the end, what the Drake equation really gives us is a sense of possibility. It takes the abstract idea of alien life and turns it into something tangible, something we can calculate and explore. It reminds us that the universe is vast and full of potential, and that we've only just begun to scratch the surface. As we continue to refine our estimates and improve our technology, the question of whether we're alone in the universe becomes less about if and more about when. With hundreds of thousands of potential life-bearing planets in our galaxy, the odds are in favor of discovery. In 2001, NASA scientists proposed a theory that sounded like something out of a science fiction novel. Alien microbes might be responsible for the red tinge on the surface of Jupiter's moon, Europa. Europa had long been a source of intrigue for astronomers, thanks to its thick shell of ice and the possibility of a liquid ocean beneath it. But this theory suggested something even more incredible: life, potentially thriving in an environment far more extreme than anything found on Earth. Europa is no ordinary moon. Its surface is a frozen, icy wasteland, with temperatures plunging to -170 degrees Celsius. Yet beneath that icy crust, scientists believe there could be a vast ocean, kept warm by volcanic activity on the ocean floor. This idea alone has made Europa one of the most promising candidates in the search for extraterrestrial life. But in 2001, researchers began to suspect that signs of life might already be visible on Europa's surface. The red streaks and blotches that crisscross Europa's ice have puzzled scientists for years. Some speculated that they were caused by minerals, like magnesium salts, rising up from the moon's interior. But when scientists analyzed the light reflected off Europa's surface using infrared spectroscopy, they found that the data didn't quite match what they expected from salts or other minerals. Something else seemed to be responsible for the way Europa reflected light, something they hadn't considered before: bacteria, specifically extremophiles, microbes that thrive in some of the harshest environments on Earth. Some of these organisms are known to survive in extreme conditions, from the crushing depths of the ocean to the intensely hot environments around hydrothermal vents. The infrared signals coming from Europa's surface had some similarities to the signatures of earthly bacteria, leading scientists to propose that microbial life might be behind the red streaks. This theory was groundbreaking. If bacteria were responsible for the red tinge on Europa's surface, it would suggest that life not only exists beneath the icy crust, but also finds its way to the surface, where it becomes flash frozen in the ice. Volcanic activity or other geological processes could periodically force liquid water from Europa's hidden ocean to the surface, bringing with it microbes from the ocean below. Once exposed to the frigid vacuum of space, these microbes would freeze almost instantly, leaving behind the red stains that have intrigued scientists for years. But could bacteria really survive in Europa's ocean, let alone on its frozen surface? Extremophiles on Earth offer a clue. Some bacteria thrive in environments with no sunlight and extreme pressure, like the deep ocean or around volcanic vents. Others survive in freezing conditions using chemical processes to generate energy instead of relying on sunlight. The possibility that similar organisms could exist on Europa is not as far-fetched as it might seem. If life does exist on Europa, it would likely be very different from anything we've seen before. The Moon's ocean is thought to be incredibly deep, up to 100 kilometers in some places, far deeper than any ocean on Earth. This immense depth, combined with the icy surface, would block any sunlight from reaching the water below. Life on Europa would have to rely on energy sources other than the sun, such as chemical reactions between the water and the rocks on the ocean floor. The idea of life surviving in such extreme conditions challenges our understanding of what life needs to thrive. For a long time, scientists assumed that life required sunlight, warm temperatures, and a stable atmosphere. But the discovery of extremophiles on Earth has shown that life can be far more adaptable than we ever imagined. If microbes can survive in the deep ocean trenches or the frozen tundra of Antarctica, then why not in Europa's hidden ocean? Of course, this theory remains speculative. While the infrared data from Europa's surface is intriguing, it's not definitive proof of life. Other explanations for the red tinge include minerals or chemical compounds that we don't yet fully understand. Still, the possibility of microbial life on Europa has made it one of the top targets for future space missions. In fact, NASA's upcoming Europa Clipper mission, set to launch in the 2020s, is specifically designed to investigate the Moon's potential for life. The spacecraft will carry a suite of instruments capable of mapping the surface, analyzing its chemical composition and searching for signs of active geological processes. While it won't be able to directly sample Europa's ocean, the Europa Clipper mission could provide crucial clues about what lies beneath the ice. Europa's red tinge is more than just a curiosity. It could be a sign of life, frozen in time on the moon's surface. If confirmed, it would represent one of the most significant discoveries in the history of science, the existence of extraterrestrial life within our own solar system. But until we can send probes or landers to directly sample the ice, the mystery of Europa's red streaks will remain just that, a mystery. Even so, the idea that life might be flourishing beneath Europa's icy shell is an exciting prospect. It forces us to rethink what we consider habitable and challenges the assumption that life can only exist in environments similar to Earth. Europa may be cold, dark, and distant, but it might also hold the key to answering one of humanity's oldest questions. Are we alone in the universe? As we continue to explore Europa, we may one day find the evidence we've been searching for, a confirmation that life can thrive in even the most extreme environments. And if life exists on Europa, what other worlds in our solar system or beyond might also harbor life in forms we've yet to imagine? In 2002, Russian scientists put forward a theory that seemed to defy everything we thought we knew about the limits of life. They proposed that a microbe known for its extraordinary resistance to radiation, Deinococcus radiodurans, might not have evolved on Earth at all, but on Mars. This hardy microbe can withstand radiation levels thousands of times higher than what would kill a human, raising the possibility that it may have originated on a planet bathed in far more cosmic radiation than Earth, Mars. To understand why Deinococcus radiodurans is so special, it helps to know just how extreme its abilities are. This microbe is often called a polyextremophile, meaning it can survive in a wide range of punishing conditions, including radiation, desiccation, and even the vacuum of space. In experiments, scientists exposed populations of this microbe to high doses of radiation, doses strong enough to kill nearly all of them. Yet, a small number survived. When the scientists repeated the process, irradiating, then allowing the survivors to reproduce, they found that after 44 rounds, the microbes had become even more resistant, needing 50 times the original dose of radiation to kill them. The question is, how could any organism evolve to withstand such intense radiation? On Earth, it would take millions, if not hundreds of millions of years, for a microbe to experience enough radiation to develop this kind of resilience. Earth, with its thick atmosphere and magnetic field, protects life from the worst of cosmic and solar radiation. But on Mars, things are different. Without a protective atmosphere, the surface of Mars is constantly bombarded by high levels of radiation. The Russian scientists theorized that Deinococcus radiodurans might have evolved under these extreme Martian conditions before being flung to Earth on a meteorite. This idea ties into the broader theory of panspermia, the hypothesis that life might travel from planet to planet, or even from one solar system to another, hitching rides on meteorites or comets. If a large asteroid struck Mars millions of years ago, it could have ejected chunks of the Martian surface into space, some of which may have eventually fallen to Earth. It's possible that Deinococcus radiodurans hitched a ride on one of these space rocks, surviving the long journey across the solar system thanks to its incredible resilience. While this theory might seem far-fetched, there's some evidence to support it. For one, we know that meteorites from Mars have made it to Earth. ALH 84001, the famous meteorite that some scientists believe contains fossilized Martian microbes, is a prime example. Secondly, experiments have shown that microbes can survive the harsh conditions of space for extended periods of time, especially if they're protected inside a rock. The journey from Mars to Earth, while difficult, is not impossible. The Russian scientists also pointed out that there hasn't been enough time in Earth's history for Deinococcus radiodurans to evolve such extreme resistance. Earth's atmosphere has protected most life from intense radiation for billions of years, meaning that the kind of radiation bombardment needed to drive this evolution simply doesn't occur here. On Mars, however, it's a different story. With no protective atmosphere and far more cosmic radiation reaching the surface, life there would have faced much higher levels of radiation, forcing microbes to adapt or perish. This theory, while compelling, remains controversial. Many scientists argue that Deinococcus radiodurans could have evolved its radiation resistance on Earth, perhaps in environments like the deep subsurface, where radiation from natural radioactive materials is higher. Others suggest that its resistance may be a byproduct of its ability to survive desiccation or drying out, a trait that would also be useful on Mars. In these scenarios, the microbe's resilience to radiation may not have evolved in response to cosmic radiation at all, but as an adaptation to survive other environmental stressors. Still, the idea that life could have originated on Mars and traveled to Earth is a fascinating one. It forces us to consider that life might not be unique to Earth. If microbes could survive the journey from Mars to Earth, could they also travel in the opposite direction? And if life can move between planets in our solar system, could it also spread to other star systems, carried by meteorites or comets across the galaxy? While the origins of Deinococcus radiodurans remain a mystery, this resilient microbe has sparked new interest in the possibility that life on Earth might have extraterrestrial roots. If microbes could survive the harsh conditions of space and travel between planets, it opens up new possibilities for where we might find life and how it might have spread across the cosmos. This theory also raises important questions about Mars itself. If Mars was once home to life, what happened to it? Did it perish when the planet's atmosphere thinned and its surface became cold and dry? Or could life still be lurking beneath the surface, shielded from the harsh radiation above? Missions like NASA's Perseverance rover are designed to search for signs of life on Mars, both past and present, and they might one day provide answers to these questions. In the end, the idea that a microbe like Deinococcus radiodurans could have come from Mars is a reminder of just how adaptable life can be. Whether it evolved on Earth or on another planet, this microbe shows us that life is capable of surviving in environments far more extreme than we once thought possible. And if life can exist on Mars, even in its harshest conditions, it raises the tantalizing possibility that life might exist elsewhere in the universe as well, on planets, moons, or even traveling through space, waiting for a chance to take root on a new world. Later, in 2002, scientists presented an idea that turned the search for life in our solar system upside down: life in the clouds of Venus. This theory was radical, considering that Venus is often seen as one of the least likely places to harbor life. With surface temperatures hot enough to melt lead and an atmosphere thick with sulfuric acid, Venus had long been thought of as a dead planet, hostile to any form of life we could imagine. But new data from NASA's Pioneer and Magellan space probes as well as Russia's Venera lander missions from the 1970s, suggested something unexpected lurking high in the planet's atmosphere. The idea that life could exist in the upper clouds of Venus is both surprising and fascinating. Around 50 kilometers above Venus's surface, the conditions are vastly different from the furnace-like environment below. Here, the temperature is a much more tolerable 70 degrees Celsius, and the pressure is comparable to that of Earth at sea level. This region of the atmosphere is more hospitable, and scientists began to wonder if something could be living there, hidden in the thick clouds that cloak the planet. The anomalies in Venus's atmosphere that hinted at life were not easily explained by any known chemical processes. First, there's the presence of carbonyl sulfide, a compound that, on Earth, is produced by biological activity or industrial processes, but is not known to form through purely inorganic means. This compound's existence in Venus's clouds raised a red flag. Could microbial life be the cause? Then there's the strange scarcity of carbon monoxide in the atmosphere. Solar radiation and lightning should be producing plenty of carbon monoxide on Venus, but instead it's rare. Something seems to be consuming it. On Earth, microbes are known to absorb carbon monoxide as part of their metabolic processes, leading scientists to wonder if something similar might be happening in Venus's upper atmosphere. Additionally, hydrogen sulfide and sulfur dioxide were detected coexisting in the clouds, which is unusual. These two gases readily react with one another and are rarely found together unless some process, potentially biological, is constantly regenerating them. Again, on Earth, microorganisms are known to play a role in cycling these chemicals. The fact that these compounds were present in the atmosphere of Venus led some researchers to hypothesize that microbes could be responsible. The theory goes like this: microbial life could exist in the relatively mild environment of Venus's upper atmosphere, floating in the clouds. These microbes would need to be highly resilient, capable of surviving the harsh chemical conditions, including the presence of sulfuric acid. But extremophiles on Earth have shown us that life can thrive in environments that seem completely inhospitable, from the acidic waters of volcanic springs to the crushing pressures of the deep ocean. If life can survive in such places on Earth, why not in the acidic clouds of Venus? This idea wasn't entirely new. Carl Sagan had speculated about the possibility of life in Venus's clouds as far back as the 1960s. But the new data from NASA and Russian probes gave the theory a fresh boost of credibility. Researchers began to seriously consider that Venus's upper atmosphere might host life, even if only in microbial form. Of course, not everyone was convinced. Many scientists pointed out that the presence of carbonyl sulfide and the other atmospheric anomalies could potentially be explained by unknown chemical processes that don't involve life. Venus's atmosphere is complex and poorly understood, and it's possible that non-biological reactions could account for the strange chemistry observed there. Still, the idea of life in the clouds of Venus remained an exciting possibility, one that warranted further exploration. In the years since the 2002 findings, the search for life in Venus's atmosphere has continued. In 2020, researchers made headlines when they detected traces of phosphine gas in the clouds of Venus. On Earth, phosphine is produced by biological processes, and its discovery on Venus reignited the debate over whether life could exist on the planet. Like the earlier detection of carbonyl sulfide, the presence of phosphine could suggest microbial life, but it could also be the result of unknown chemical reactions. As with many aspects of the search for extraterrestrial life, the evidence is intriguing but inconclusive. One thing is certain: the idea that Venus could harbor life, even in its clouds, forces us to rethink what we consider habitable. For decades, the search for life has focused primarily on planets and moons, with conditions similar to those on Earth. Places where liquid water exists, where the temperature is moderate, and where the atmosphere is stable. But the possibility of life on Venus shows that life might not need to conform to our expectations. It might be able to thrive in environments that seem utterly alien to us. The search for life in Venus's clouds is far from over. New missions are being proposed that would send probes to the planet to directly sample its atmosphere, searching for signs of microbial life. These missions could provide the data we need to either confirm or debunk the theory once and for all. Until then, Venus remains one of the most mysterious and potentially habitable worlds in our solar system. Whether or not life exists in Venus's atmosphere, the very idea challenges us to think more broadly about where life might be found. We now know that life can survive in extreme environments on Earth, from the icy depths of the Antarctic to the scalding waters of undersea volcanoes. If life can exist in these harsh environments, there's no reason it couldn't exist elsewhere in the solar system, in places like the icy moons of Jupiter, or, yes, even in the clouds of Venus. In 2003, a team of Italian scientists proposed an exciting and controversial theory. Sulfur deposits on Jupiter's moon Europa could be the waste products of underground bacterial colonies. Europa, with its icy surface and suspected subsurface ocean, has long been one of the most intriguing targets in the search for extraterrestrial life. But this new theory suggested that signs of life might not be buried deep beneath the ice after all. They might be sitting on the surface, hidden in plain sight. Europa's icy shell has captivated scientists for decades. Beneath that ice, stretching for kilometers in some places, lies a vast ocean of liquid water. This ocean is thought to be kept warm by volcanic activity on the ocean floor, creating an environment where life might thrive. On Earth, deep-sea hydrothermal vents teem with life despite the extreme conditions: no sunlight, high pressure, and heat. If similar conditions exist on Europa, the logic goes, microbial life could flourish there as well. But the surface of Europa, covered in bright white ice with streaks of brown and yellowish sulfur deposits, provides another clue. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, detected sulfur compounds on Europa's surface. These sulfur traces intrigued scientists because they looked strikingly similar to waste products produced by bacteria here on Earth, specifically bacteria that survive in icy environments. In lakes beneath the ice of Antarctica, for example, bacteria feed on sulfur compounds, and as they metabolize, they produce sulfur waste, which gets locked into the ice. The sulfur found on Europa's surface could be the result of a similar process, suggesting that bacteria might be living below the moon's icy crust, near the ocean floor, where volcanic activity provides heat and nutrients. Here's where the theory gets even more interesting. It's possible that geological processes on Europa are periodically churning the ice, bringing material from the subsurface ocean up to the surface. As the ice moves, it could be transporting bacterial waste products, along with the bacteria themselves, from the depths of the ocean to the surface, where they freeze in the cold vacuum of space. This would explain the presence of sulfur on the surface and provide a tantalizing clue that life might exist beneath the ice. The similarities between Europa's sulfur and the waste products of Earth's bacteria gave the Italian scientists reason to believe that life could be the explanation for these surface deposits. But not everyone was convinced. Some researchers pointed out that sulfur is also abundant on Jupiter's volcanic moon Io, and it's possible that sulfur from Io's volcanoes could have made its way to Europa, depositing itself on the icy moon's surface. In this case, the sulfur wouldn't be biological at all. It would simply be another geological feature of the Jovian system. Despite the debate, the theory that life might exist beneath Europa's icy surface remains one of the most compelling in the search for extraterrestrial life. Europa's ocean is shielded from the harsh radiation that bombards the moon's surface, making it a potentially habitable environment. If bacteria or other microorganisms are living in that ocean, they would need an energy source to survive, and volcanic activity could provide the heat and chemicals necessary for life to thrive in the dark, sunless depths. If the sulfur on Europa's surface does turn out to be biological in origin, it would represent some of the most direct evidence of life beyond Earth that we've ever discovered. But as with many of the tantalizing clues in the search for extraterrestrial life, it remains just that, a clue. Without the ability to directly sample Europa's ocean or ice, we can't say for certain whether the sulfur is the result of geological or biological processes. That's where future missions come in. NASA's Europa Clipper mission, set to launch in the 2020s, will provide new data on the moon's surface and subsurface ocean. The spacecraft will carry instruments designed to analyze Europa's ice and atmosphere in greater detail than ever before. While the Europa Clipper won't land on the moon or drill through the ice to reach the ocean, it will be able to detect signs of organic compounds, chemical processes, and possibly even plumes of water vapor erupting from cracks in the ice. If the mission finds evidence of biological activity, it could be the first step toward answering one of humanity's oldest questions: is there life beyond Earth? Europa has long been considered one of the best places to look for extraterrestrial life in our solar system, and the possibility of microbial life in its ocean continues to fuel our curiosity. Whether the sulfur deposits on the surface are a sign of life or not, the moon's ocean remains a prime target for future exploration. If life can thrive in Europa's dark, icy depths, it would fundamentally change our understanding of where life can exist and what forms it might take. The idea that bacteria could survive beneath Europa's ice, producing sulfur waste that gets transported to the surface, challenges our assumptions about the kinds of environments that can support life. It shows us that life might not need sunlight or a temperate climate. It might only need water, heat, and a source of chemical energy. As we continue to study Europa and other icy moons in the outer solar system, we're learning that life could exist in places we once thought impossible. The discovery of extremophiles on Earth, capable of surviving in environments that are hostile to most life forms, has expanded our understanding of what life needs to survive. And if life can exist in the extreme environments of Earth, it could exist in the deep oceans of Europa, surviving off the energy from volcanic vents, just as it does here. The search for life on Europa isn't just about finding bacteria on a distant moon. It's about expanding our horizons, pushing the boundaries of what we think is possible, and opening our minds to the idea that life, in all its forms, might be far more common in the universe than we ever imagined. In 2004, a discovery on Mars reignited one of the most pressing questions in the search for extraterrestrial life. Could life still exist on the Red Planet? 3 independent research teams, using data from Earth-based telescopes and the European Space Agency's Mars Express orbiter, detected something unexpected: methane in the Martian atmosphere. On Earth, methane is primarily produced by biological processes, so the presence of this gas on Mars hinted at something potentially extraordinary. Could microbial life still be active beneath the Martian surface? Methane is a relatively simple molecule, but it's also unstable in the Martian atmosphere, where ultraviolet light from the sun quickly breaks it down. For methane to be present at detectable levels, it must have been produced recently. This raised an exciting possibility. Something on Mars is producing methane right now. There are 2 main processes that could explain the presence of methane: geological activity or biological activity. Volcanic eruptions, for instance, can release methane, as can the chemical interaction of water with certain types of rock deep underground. The problem is, there's no direct evidence of active volcanism on Mars today. The planet's volcanoes have been dormant for millions of years, and there haven't been any significant signs of recent volcanic activity. That left scientists with an even more tantalizing possibility. The methane could be a byproduct of microbial life living beneath the surface of Mars. On Earth, certain types of bacteria, known as methanogens, produce methane as a metabolic byproduct. These bacteria thrive in environments without oxygen, living in the deep subsurface or in the guts of animals. If similar bacteria exist on Mars, they could be producing the methane detected in the atmosphere. The idea that life might exist beneath the Martian surface is not as far-fetched as it might sound. Mars was once a much warmer and wetter planet, with rivers, lakes, and perhaps even oceans covering its surface. But as the planet's atmosphere thinned, the surface became colder and more hostile. It's possible, however, that microbial life, if it existed, retreated underground, where it could be shielded from radiation and survive in pockets of liquid water that might still exist today. What makes the methane discovery even more interesting is that it's not evenly distributed across the planet. The concentration of methane appears to vary by location and season, suggesting that its source is localized and potentially tied to specific regions of Mars. This seasonal variation could be the result of subsurface microbial colonies becoming more active at certain times of the year, releasing methane into the atmosphere as a byproduct of their metabolism. Of course, there are non-biological explanations for the methane as well. The gas could be the result of geological processes we don't yet fully understand, such as the slow release of methane from frozen underground reservoirs known as clathraites, or the interaction of water and rock in a process known as serpentinization. But these processes would still require a source of water, which raises another key question: how much liquid water exists beneath the surface of Mars? The detection of methane has shifted the focus of Mars exploration. NASA's Curiosity rover, which landed on Mars in 2012, has since confirmed that methane is present in the atmosphere and has detected seasonal variations in its levels. This discovery has driven scientists to investigate specific regions where the methane seems to be concentrated, in the hope of finding more direct evidence of its origin. One of the leading hypotheses is that the methane could be coming from underground aquifers, pockets of liquid water trapped beneath the surface. If this is the case, these aquifers could provide a habitable environment for microbes, much like the deep underground ecosystems we see on Earth. But without drilling into the Martian subsurface, we can't be sure if these aquifers exist or if they might support life. Adding another layer of intrigue, in 2005, a European Space Agency scientist claimed to have found evidence of formaldehyde in the Martian atmosphere, which could be produced by the oxidation of methane. If confirmed, this would suggest that a whopping 2.5 million tons of methane are being produced on Mars every year, far more than could be explained by non-biological processes alone. This controversial finding has yet to be confirmed by other missions, but it points to the need for more detailed exploration of the Martian atmosphere. The discovery of methane on Mars has reignited interest in the red planet as a potential habitat for life, both past and present. While we still don't have definitive proof of Martian life, the methane detection suggests that something is happening beneath the planet's surface, and it could be microbial activity. Future missions to Mars, including NASA's Perseverance rover, which landed in 2021, are designed to search for signs of ancient life and study the planet's geology in greater detail. Perseverance is equipped with instruments that can analyze the chemical composition of rocks and soil, searching for organic molecules and biosignatures that might point to past or present life. It's also tasked with collecting samples that could one day be returned to Earth, giving scientists the chance to study Martian material in a controlled laboratory environment. The search for life on Mars has always been a central goal of space exploration, but the discovery of methane has brought us closer than ever to answering the question of whether life might still exist there. If future missions confirm that methane is being produced by living organisms, it would be one of the most significant discoveries in human history. But until we can pinpoint the exact source of the methane, we're left with a mystery, one that continues to drive exploration and fuel our curiosity about what lies beneath the surface of Mars. Whether it's microbial life or a previously unknown geological process, the presence of methane on Mars is a sign that the planet is more dynamic than we once thought. In February 2004, something curious happened that once again stirred the excitement of astronomers and alien hunters alike. While scanning the skies for extraterrestrial signals, the SETI project stumbled upon a mysterious radio signal from a region of space between the constellations Pisces and Aries. This wasn't the first time SETI had detected unexplained signals, but this one was different. The signal had appeared not once, but 3 times, all from the same spot in the sky, and it was one of the best candidates yet for potential alien communication. The search for extraterrestrial signals has been ongoing for decades. Using massive radio telescopes, astronomers scan the cosmos for anything unusual, anything that might suggest intelligent life trying to communicate with us. Most of the time, they find nothing but background noise or signals from human-made sources, like satellites. But this time, the signal SETI picked up didn't fit the usual patterns. It was unusual enough that it warranted deeper investigation. The signal came from an empty part of space where there were no known stars or planets, just the cold, dark void between celestial bodies. What made it particularly intriguing was its frequency. It was detected at a frequency of 1420 MHz, the radio frequency at which hydrogen, the most abundant element in the universe, absorbs and emits energy. Many scientists believe that if an advanced alien civilization wanted to communicate across the vast distances of space, this frequency would be a logical choice. as it would be easily recognizable by anyone with knowledge of the universe's most fundamental building blocks. What made the signal even more mysterious was its narrow frequency band. Natural sources of radio waves, such as pulsars or quasars, tend to emit across a wide range of frequencies. This signal, however, was confined to a very specific range, suggesting it might not be a natural phenomenon. In other words, it seemed more like a deliberate transmission than a random cosmic event. While it's easy to jump to the conclusion that this signal might be the work of an alien civilization, the scientific community is far more cautious. There are many possible explanations for unexplained radio signals, including previously unknown astronomical phenomena or interference from human-made sources. But the fact that this signal was detected 3 times, all from the same location, made it stand out from the usual background noise. Could it be that someone or something was trying to communicate with us? One of the challenges with detecting potential alien signals is the difficulty in following up. The vastness of space and the sheer number of signals being transmitted at any given moment make it incredibly difficult to isolate and study specific transmissions. Despite repeated attempts to locate the signal again, SETI hasn't detected it since 2004. The disappearance of the signal has only added to its mystery. Some researchers have suggested that the signal could be the result of a previously unknown natural phenomenon, perhaps something similar to the pulsars that were first discovered in the 1960s and initially thought to be artificial. But without more data, it's impossible to say for sure. The lack of any known stars or planets in the direction of the signal only deepens the puzzle. If this was a transmission from an alien civilization, why would they be located in such an empty part of space? Could they be using a technology or strategy we don't yet understand? There's also the possibility that the signal was a one-time event, perhaps a brief intentional message sent out across the cosmos. If an alien civilization wanted to make contact with other intelligent beings, they might send out periodic signals in hopes of being discovered. Or it could be that the civilization responsible for the signal no longer exists, having perished in the time it took for their message to reach us. Despite the lack of concrete answers, the 2004 SETI signal remains one of the most intriguing pieces of evidence in the ongoing search for extraterrestrial intelligence. It shows that while we haven't yet found definitive proof of alien life, there are still mysteries out there that challenge our understanding of the universe. The search for extraterrestrial signals continues, with scientists around the world using increasingly sophisticated technology to scan the skies for anything that might suggest we are not alone. In recent years, projects like Breakthrough Listen have expanded the search for extraterrestrial signals, using powerful radio telescopes to monitor millions of stars for signs of intelligent life. These projects are capable of detecting even faint transmissions from distant planets, increasing the chances that we might one day find a signal like the one detected in 2004, but this time with enough information to study it in detail. The discovery of a genuine extraterrestrial signal would be a monumental moment in human history. It would confirm that intelligent life exists beyond Earth, reshaping our understanding of our place in the cosmos. But until we can confirm that such signals are indeed from intelligent beings, we're left with tantalizing clues and more questions than answers. The 2004 SETI signal reminds us that the universe is a vast and mysterious place. We've only just begun to explore it, and there's still so much we don't know. In 2011, NASA astrobiologist Richard Hoover made headlines with a bold and controversial claim. he had found fossilized evidence of extraterrestrial life in meteorites. Hoover's study, published in the Journal of Cosmology, suggested that microscopic fossils resembling cyanobacteria, tiny, single-celled organisms found on Earth, were embedded in meteorites that had fallen to our planet from space. If true, this discovery would be nothing short of groundbreaking, offering the first tangible proof that life exists beyond Earth. Cyanobacteria are some of the oldest known organisms on our planet, dating back billions of years. These hardy microbes played a key role in shaping Earth's atmosphere, producing oxygen through photosynthesis and setting the stage for more complex life to evolve. If similar organisms were found in meteorites, it would suggest that life isn't confined to Earth, that it may be a common phenomenon in the universe. Hoover's claims centered around meteorites known as carbonaceous chondrites, which are rich in carbon compounds and water. These meteorites are believed to be some of the oldest and most primitive objects in the solar system, having formed around 4.5 billion years ago, at the birth of the solar system. Hoover's analysis of these meteorites using scanning electron microscopes revealed what he described as tiny filaments and structures that resembled the fossils of cyanobacteria found on Earth. The idea that meteorites could contain evidence of extraterrestrial life is rooted in the theory of panspermia, the hypothesis that life can travel between planets, hitching a ride on comets, asteroids, or meteorites. According to this theory, life might not have originated on Earth, but instead could have been delivered here from space billions of years ago. If life can survive the journey through the harsh conditions of space, it might explain how life could spread across the universe from planet to planet, or even from one solar system to another. But Hoover's discovery was not without controversy. The Journal of Cosmology, where his study was published, has been criticized for its lack of rigorous peer review, and many scientists were skeptical of Hoover's conclusions. Critics argued that the filaments Hoover identified as fossilized microbes could be the result of contamination from Earth. After all, meteorites that fall to Earth are often exposed to the elements and can become contaminated by terrestrial microbes. Hoover, however, maintained that the structures he found were deeply embedded within the meteorites, suggesting that they were not the result of contamination, but had formed long before the meteorites landed on Earth. Another challenge to Hoover's findings came from the scientific community's cautious approach to extraordinary claims. As Carl Sagan famously said, extraordinary claims require extraordinary evidence. For many scientists, Hoover's study lacked the rigorous testing and verification needed to confirm that the filaments were indeed fossilized extraterrestrial microbes. They pointed out that while the structures in the meteorites resembled cyanobacteria, resemblance alone wasn't enough to prove their origin. More concrete evidence would be needed, such as the discovery of biomolecules or isotopic signatures that couldn't be explained by contamination from Earth. Despite the skepticism, Hoover's study reignited interest in the idea that life could be found in meteorites. Other researchers have continued to investigate the possibility that meteorites might contain the building blocks of life or even evidence of ancient extraterrestrial organisms. In fact, meteorites have been known to contain organic compounds, such as amino acids, which are the building blocks of proteins and essential components of life as we know it. But finding fully formed fossilized microbes would be another level of discovery entirely. The debate over Hoover's claims also highlights one of the central challenges in the search for extraterrestrial life, distinguishing between life that might have originated elsewhere in the cosmos and life that could have contaminated samples after they arrived on Earth. It's a tricky balance, as space rocks and other celestial bodies inevitably interact with Earth's biosphere when they enter our planet's atmosphere. This makes it difficult to conclusively determine whether something found in a meteorite is truly extraterrestrial. Despite these challenges, the possibility that meteorites could carry evidence of life from other planets continues to inspire scientists. Meteorites offer a unique opportunity to study material from the far reaches of the solar system, including from places we haven't yet visited with spacecraft. If life ever existed on Mars, for example, meteorites blasted off the planet's surface during ancient collisions could have carried traces of Martian microbes to Earth. Similarly, meteorites from distant asteroids or comets might offer clues about the conditions under which life could have arisen elsewhere in the solar system. While Hoover's study remains a subject of debate, it has opened the door to further research into the possibility that life exists beyond Earth. Missions like NASA's OSIRIS-REx, which has collected samples from the asteroid Bennu, and future missions to Mars that aim to return samples of Martian soil to Earth, are designed to address these questions in a more rigorous way. By analyzing samples in controlled laboratory environments, scientists hope to avoid the issues of contamination that have complicated earlier studies. The potential discovery of life in meteorites forces us to reconsider our understanding of how life could spread across the cosmos. If microbes can survive the journey through space, then life might be far more common than we once thought. It's possible that the same meteorites that delivered the building blocks of life to Earth could have seeded life on other planets as well. And if life can travel between planets, the universe might be teeming with microbial life, quietly waiting for us to discover it. For now, the question of whether Hoover's fossilized microbes are truly extraterrestrial remains unanswered. But the possibility that meteorites could carry evidence of life from other worlds keeps pushing the boundaries of what we know and what we think is possible. In 2020, NASA's chief scientist, Dr. Ellen Stofan, made a bold prediction that sent ripples through the scientific community and beyond. During a panel discussion, she stated that humanity is on the verge of discovering alien life, not centuries away, but potentially within the next 20 to 30 years. This wasn't speculation from a sci-fi novel. It was a statement from one of the top scientific minds at NASA. The prediction wasn't about intelligent beings visiting us in flying saucers, but rather microbial life, likely lurking in the icy moons of our solar system or on distant exoplanets. We know where to look. We know how to look, Dr. Stofan said. In most cases, we have the technology, and we're on a path to implementing it. Her optimism wasn't unfounded. Recent discoveries in space exploration, combined with technological advancements, have dramatically increased our chances of detecting life beyond Earth. Dr. Stofan wasn't alone in her bold prediction. Other scientists on the panel shared her optimism, including John Grunsfeld, a former astronaut and NASA's associate administrator for the Science Mission Directorate. Grunsfeld echoed the sentiment, noting that we are likely one generation away from finding life within our solar system, particularly on planets like Mars, or icy moons such as Europa or Enceladus. These moons are now considered prime candidates in the search for alien life because of their subsurface oceans and the potential for hydrothermal activity, conditions that on Earth have proven to be fertile grounds for life. Mars, too, remains at the forefront of the search. Decades of research and exploration have shown that the planet was once warmer and wetter, with liquid water flowing across its surface, possibly long enough for microbial life to develop. While the surface of Mars today is cold and barren, Some scientists believe that life could still exist below the surface, where liquid water might persist in aquifers protected from the harsh radiation. Another key factor driving this optimism is the discovery of planets beyond our solar system, exoplanets that lie in the habitable zones of their stars. In recent years, astronomers have identified thousands of these planets, some of which have the right conditions for liquid water and potentially life. In 2020, astronomers studying an exoplanet called K2-18b detected potential signs of water vapor in its atmosphere, sparking excitement that this distant world might host conditions suitable for life. In addition to water vapor, scientists are looking for biosignatures, chemical compounds like methane, oxygen, or even industrial pollutants that could indicate the presence of life. One such discovery came in 2020 when astronomers detected traces of phosphine gas in the clouds of Venus. Phosphine is a compound associated with biological processes on Earth, and its detection on Venus, a planet with conditions seemingly too harsh for life, renewed the debate over whether microbial life could exist in Venus's upper atmosphere, where temperatures and pressures are more moderate. The phosphine discovery was met with skepticism by some scientists who pointed out that the gas could be produced by unknown chemical processes. Nevertheless, it reignited interest in the possibility of life on Venus, a planet long thought to be inhospitable to life in any form. Whether or not life exists on Venus, the discovery of phosphine shows that our ability to detect biosignatures is rapidly improving, increasing the likelihood that we will find evidence of life elsewhere in the coming decades. What's particularly exciting is that the search for life is no longer limited to our solar system. With telescopes like the James Webb Space Telescope now in operation, astronomers can study the atmospheres of exoplanets in unprecedented detail. JWST is capable of detecting the chemical composition of distant planets' atmospheres, providing clues about their habitability. If an exoplanet has a high concentration of oxygen or methane, for example, it could suggest biological processes at work. The advances in space exploration, both in our solar system and beyond, have brought us closer than ever to answering the age-old question, are we alone? And while Dr. Stofan's prediction about finding life within 20 to 30 years is ambitious, it's based on a solid foundation of scientific discovery and technological progress. Part of what makes this prediction so exciting is that it doesn't rely on one specific discovery, but rather a combination of them. Between Mars' ancient history of liquid water, the subsurface oceans of Europa and Enceladus, and the thousands of potentially habitable exoplanets, scientists have more leads than ever before. Each of these worlds offers a unique opportunity to find life, and as we continue to develop more advanced tools to explore them, the chances of success grow. However, it's important to note that when Dr. Stofan and her colleagues talk about finding life, they aren't necessarily referring to complex organisms or intelligent civilizations. The most likely form of alien life we'll discover in the near future is microbial, simple, single-celled organisms like bacteria. But even this would be a monumental discovery, one that would reshape our understanding of life's place in the universe. The discovery of microbial life beyond Earth would have profound implications. It would suggest that life might be common in the universe and that wherever the right conditions exist, water, energy, and the right chemistry, life has the potential to arise. It would also challenge us to think differently about the search for more complex forms of life. If microbes can exist on other planets or moons, it opens the door to the possibility that more advanced life forms might be out there too, perhaps on planets we haven't even discovered yet. For now, the search continues. And while we have no definitive evidence of extraterrestrial life, the clues are starting to add up. As Dr. Stofan said, it's not an if, it's a when. With each new discovery, we inch closer to finding the answer. And if that answer comes within the next 20 to 30 years, as NASA predicts, it will be one of the most transformative moments in human history. As we close this deep dive into the most intriguing alien facts and discoveries of the last few decades, it's clear that the question of whether we are alone in the universe is not just speculative, it's increasingly grounded in scientific inquiry. We've explored 12 fascinating moments in human history, where the search for extraterrestrial life took giant leaps forward. From the discovery of chemical signatures on Mars to the detection of mysterious radio signals from deep space. Each discovery, while not definitive proof of alien life, adds a new piece to the puzzle, edging us closer to an answer. The search for life beyond Earth is a story of persistence, curiosity, and scientific rigor. It's a journey that spans disciplines, from astrobiology to astronomy, and requires the collaboration of thousands of scientists, engineers, and researchers across the globe. What makes this search so compelling isn't just the potential for finding life, but the way each discovery forces us to expand our understanding of the universe and reconsider the possibilities of where and how life might exist. We began our journey in 1976, when NASA's Viking landers touched down on Mars and conducted the first biological experiments on Martian soil. The results were tantalizing. Chemical signatures indicative of life, or so it seemed. The Viking landers performed an experiment that suggested some form of metabolism was taking place in the Martian soil, a potential indicator of microbial life. Yet, other experiments on board failed to find the organic molecules that would be expected if life were present. NASA ultimately declared the results inconclusive, calling it a false positive. But that decision didn't sit well with everyone. Some scientists, including Gilbert Levine, who designed the experiment, still believe that the Viking landers may have detected life, and that our technology at the time simply wasn't advanced enough to confirm it. The implications of those 1976 experiments are still being debated, but they opened the door for future missions to Mars, each one armed with more sophisticated instruments capable of analyzing Martian soil and atmosphere in greater detail. The Viking landers' findings were a critical first step in what would become one of the most enduring quests in the search for life: Mars as a potential home for microbial life, past or present. Fast forward to 1977, when one of the most famous and mysterious signals in the search for extraterrestrial intelligence was detected: the WOW signal. Detected by Ohio State University's Big Ear radio telescope, the signal was so extraordinary that an astronomer monitoring the data scribbled "WOW" in the margin of the printout. For 37 seconds, a powerful narrowband signal originating from deep space was detected, and it seemed like it could have been an intentional message. It was detected in the hydrogen frequency, a universal constant that any intelligent civilization would likely recognize. Yet, despite numerous follow-up attempts, the WOW signal was never heard again. Whether it was an artificial transmission or a natural cosmic phenomenon remains one of the great unsolved mysteries in the search for alien life. In 1996, another potential breakthrough captured headlines when NASA scientists claimed to have found fossilized microbial life in a Martian meteorite known as ALH84001, discovered in Antarctica. The meteorite, believed to have been ejected from Mars and traveled to Earth over millions of years, contained tiny structures that resembled nanobacteria. Coupled with the discovery of organic molecules and magnetite crystals, the findings pointed to the possibility that life may have existed on Mars billions of years ago. However, like many of the discoveries in this field, skepticism followed. Some experts suggested that the nanobacteria-like structures could have been formed by non-biological processes, and the evidence has since been challenged. But even so, ALH84001 remains a key moment in the ongoing debate about whether Mars ever harbored life. As we moved into the early 2000s, the search for life beyond Earth expanded beyond our own planet. In 2001, a new analysis of the Drake equation, first formulated by radio astronomer Frank Drake in 1961, revised the number of potential life-bearing planets in the Milky Way. Using new data from space telescopes and a better understanding of planetary systems, scientists estimated that there could be hundreds of thousands of planets in our galaxy capable of supporting life. The Drake equation provided a framework for understanding the factors that might influence the development of intelligent civilizations, and the updated calculations suggested that life could be much more common than we previously thought. If the universe is teeming with planets in the so-called Goldilocks zone, where conditions are just right for life, then the question is not whether life exists, but how much of it is out there waiting to be discovered. That same year, another intriguing theory surfaced, this time regarding Jupiter's moon Europa. Scientists had long suspected that Europa, with its vast subsurface ocean hidden beneath a thick layer of ice, could be one of the best places to search for life. But in 2001, NASA researchers proposed that the red tinge on Europa's icy surface might be caused by frozen microbes. The strange infrared signature coming from Europa's surface didn't match any known minerals, but it did bear a resemblance to the spectra of extremophiles on Earth, microbes that thrive in extreme conditions. If microbial life exists in the deep, dark oceans beneath Europa's ice, it could occasionally be brought to the surface by geological processes, where it would freeze, leaving behind evidence of its existence. The following year, in 2002, Russian scientists made waves with a radical claim: the super-hardy bacterium Deinococcus radiodurans, capable of surviving thousands of times the radiation dose that would kill a human, might have evolved on Mars. Their experiments showed that Deinococcus could become even more radiation-resistant through repeated exposure. But such extreme resistance was unlikely to have evolved on Earth, where radiation levels are relatively low. By contrast, Mars' surface is bombarded with radiation, which could have driven the evolution of such a resilient microbe. The Russian scientists suggested that Deinococcus might have been flung to Earth on a meteorite, sparking new discussions about panspermia, the idea that life could travel between planets, spreading across the cosmos. In that same year, scientists began to explore the possibility of life in the unlikeliest of places, Venus. The idea that Venus, with its scorching surface temperatures and clouds of sulfuric acid, could harbor life seemed absurd at first. But in 2002, researchers detected strange chemical anomalies in Venus's atmosphere. Solar radiation and lightning should have been generating carbon monoxide in the atmosphere, yet it was mysteriously absent. The presence of hydrogen sulfide and sulfur dioxide, gases that shouldn't coexist, suggested that something unusual was happening. Most curious of all was the detection of carbonyl sulfide, a compound that on Earth is produced by biological processes. Could it be that microbial life exists in the temperate zone high in Venus's clouds, where conditions are more hospitable than the planet's hellish surface? In 2003, attention returned to Europa with another exciting theory. The sulfur deposits on the Moon's surface might be the waste products of underground bacterial colonies. Sulfur, detected by the Galileo spacecraft, was thought to be coming from Europa's subsurface ocean, possibly spewed out by volcanic activity and frozen on the surface. The similarity between Europa's sulfur and the waste products of bacteria on Earth pointed to the possibility of life in Europa's hidden ocean. If true, this would represent one of the most direct signs of extraterrestrial life in our solar system, though the debate over Europa's sulfur is still ongoing. Mars made headlines again in 2004 when scientists detected methane in the planet's atmosphere. Methane is a gas that, on Earth, is largely produced by biological processes, and its presence on Mars raised the possibility that microbial life could still be active there. While geological processes like volcanism could also explain the methane, the seasonal variations in methane concentrations suggested a more complex origin. Could it be that microbes are producing methane beneath the Martian surface, where pockets of liquid water might exist? The discovery of methane pushed Mars back into the spotlight as one of the most promising places to search for life. Also in 2004, a mysterious radio signal was detected by SETI, the Search for Extraterrestrial Intelligence. The signal was picked up 3 times from the same region of space, near the constellations Pisces and Aries. While natural cosmic phenomena can produce radio waves, this signal stood out because of its narrow frequency range, which suggested it could be artificial. The signal remains unexplained, adding to the growing list of mysterious radio transmissions that could potentially be signs of intelligent life trying to reach out across the stars. In 2011, NASA astrobiologist Richard Hoover made a bold claim that shook the scientific community. He had found fossilized microbial life in meteorites. Hoover's study, published in the Journal of Cosmology, suggested that the meteorites contained tiny structures resembling cyanobacteria, ancient organisms that once thrived on Earth. If these structures were indeed extraterrestrial, it would mean that life had traveled through space, possibly carried by meteorites or comets. However, Hoover's findings were met with skepticism, with many scientists pointing out the possibility of contamination from Earth. Despite the controversy, Hoover's work reignited interest in the idea that life could exist, or have existed, beyond Earth, traveling across the cosmos on space rocks. Finally, we come to the bold predictions made by NASA in 2020. During a panel discussion, NASA's chief scientist, Dr. Ellen Stofan, predicted that humanity could find strong evidence of alien life within the next 20 to 30 years. With missions to Mars, Europa, and beyond, coupled with the discovery of thousands of potentially habitable exoplanets, Stofan's prediction wasn't mere speculation. It was grounded in the rapid advancements being made in space exploration. The search for biosignatures, such as methane or oxygen in the atmospheres of distant planets, combined with new data from missions like the James Webb Space Telescope, has brought us closer than ever to answering the question, are we alone? As we conclude our exploration of the evidence, theories, and milestones in the search for alien life, it's clear that the story is far from complete. Every discovery, every signal, every tantalizing clue raises new questions and pushes the boundaries of our understanding. But what does this all mean for the future? How do we, as a species, move forward from here? The outlook, while full of uncertainty, remains deeply optimistic. The pursuit of extraterrestrial life isn't just about finding life on other planets. It's about confronting the profound mysteries of existence, exploring new horizons of science and technology, and ultimately reshaping our understanding of the universe and ourselves. The search for life beyond Earth is no longer the domain of speculative fiction or wishful thinking. It's a central goal of many modern space missions, driven by new technologies, scientific advancements, and a growing consensus that life elsewhere might be more plausible than previously imagined. Moving forward, humanity faces some critical shifts in how we approach this search, how we process its implications, and what it could mean for our collective future. The field of astrobiology, once viewed as speculative, has become a cornerstone of planetary science. Moving forward, astrobiology will likely see increased attention, funding, and collaboration from a wide range of disciplines. The days of isolated research are over. Biologists, chemists, physicists, engineers, and planetary scientists now work in tandem to explore the possibility of life beyond Earth, creating an interdisciplinary approach to one of humanity's oldest questions. One of the most immediate shifts in scientific focus will likely involve missions to planets and moons within our own solar system. The discovery of potential biosignatures on Mars, Europa, and Enceladus has already shifted priorities at NASA, the European Space Agency, and other space organizations worldwide. New missions are being planned with more advanced instrumentation specifically designed to detect life. The James Webb Space Telescope, for instance, is not just looking for exoplanets, it's also scanning their atmospheres for gases like methane and oxygen, potential signs of biological processes. In the coming decades, space agencies will likely focus on sending missions designed to sample the icy crusts of moons like Europa or dive through the methane lakes of Titan. These moons, once considered lifeless rocks, are now top contenders for hosting microbial life in their subsurface oceans. Space probes equipped with sophisticated sensors will penetrate these icy worlds to search for organic molecules or signs of biological processes. This shift in focus indicates a growing optimism in the scientific community. Life may not just exist on other planets. It might be hiding right under our noses within our own solar system. Moving forward, technological advancements will play a critical role in the search for extraterrestrial life. We are in the midst of a technological revolution that is reshaping how we explore space. One of the most transformative technologies is the development of autonomous robots and drones, which will allow us to explore environments too hostile or distant for human astronauts. The Perseverance rover on Mars, for example, is currently collecting rock samples that might one day be returned to Earth for analysis, an essential step in the search for past life on Mars. Similar technologies will be crucial for missions to places like Europa and Titan, where human exploration is impossible given current capabilities. Artificial intelligence is also poised to revolutionize space exploration. AI can analyze vast amounts of data far faster and more efficiently than human scientists. As we gather more data from exoplanets, moons, and distant galaxies. AI will be essential for detecting patterns and anomalies that might indicate the presence of life. In the future, AI systems could autonomously identify promising sites for exploration, simulate alien environments, or even assist in the development of life-detecting instruments. Another promising development is in propulsion technology. Currently, our exploration of the universe is limited by the immense distances between celestial bodies. However, advances in propulsion systems such as ion propulsion, solar sails, or even the theoretical warp drives could drastically reduce travel times and allow us to explore distant worlds more efficiently. In the long term, faster and more energy-efficient space travel will expand the scope of the search, enabling us to visit more distant planets, moons, and even other star systems. The discovery of thousands of exoplanets has fundamentally changed our understanding of the universe and reshaped the search for extraterrestrial life. Moving forward, this exoplanet revolution will only intensify. The Kepler Space Telescope opened the floodgates, showing us that planets are not rare. They are everywhere. Many of these planets are located in the habitable zone, the region around a star where conditions might be right for liquid water to exist, a key ingredient for life as we know it. Next-generation space telescopes like the James Webb Space Telescope and the planned Large UV Optical Infrared Surveyor will give us unprecedented views of these distant worlds. By analyzing the light passing through exoplanet atmospheres, these telescopes can detect the chemical signatures of life. The presence of gases like oxygen, methane, and carbon dioxide in an exoplanet's atmosphere could provide strong evidence of biological processes at work. With these technologies, we may soon be able to narrow down the search to a handful of planets where the conditions for life seem most promising. The question moving forward isn't whether we will find potentially habitable exoplanets, but what happens when we do? How will we explore these distant worlds? Could we one day send probes to another star system, perhaps using technologies like laser-powered light sails or fusion propulsion? While this kind of exploration may be centuries away, the seeds are being planted now. The discoveries we make over the next few decades will lay the groundwork for the long-term exploration of the galaxy. The discovery of alien life, even in its most basic form, would have profound implications for human society. Moving forward, we must prepare ourselves for how such a discovery would impact our worldview, our cultures, and our sense of identity. First and foremost, the discovery of extraterrestrial life would force us to confront the notion that we are not unique. For centuries, humans have viewed themselves as the center of the universe, a privileged species in a vast empty cosmos. But if we find even the simplest form of life on another planet, that narrative changes. We become one of many, a small part of a much larger and more complex cosmic ecosystem. This shift in perspective could lead to a profound rethinking of our place in the universe. Philosophers and ethicists have long pondered what it would mean to discover alien life. Some argue that it could lead to a new era of humility and cooperation as humanity grapples with its newfound place in the cosmic hierarchy. Others warn that it could exacerbate tensions as nations and groups compete for control over the exploration and potential resources of alien worlds. Religious institutions may also face significant challenges. While some belief systems might easily integrate the discovery of extraterrestrial life into their cosmologies, others could struggle to reconcile their doctrines with the existence of life beyond Earth. However, History has shown that religions can evolve in response to new scientific discoveries. When Galileo demonstrated that Earth was not the center of the universe, it initially provoked a backlash. But over time, many religious traditions adapted to this new understanding of the cosmos. The discovery of alien life may provoke similar shifts in thinking, leading to new interpretations of creation, existence, and the divine. Popular culture, too, will play a major role in how we process the discovery of extraterrestrial life. For decades, science fiction has shaped our expectations of what aliens might look like, how they might communicate, and what their civilizations might be like. While these depictions are often fantastical, they have prepared us to think about the possibility of life beyond Earth in a way that would have been unimaginable a century ago. Moving forward, as we uncover more evidence of alien life, popular culture will continue to evolve, reflecting our hopes, fears, and curiosities about the unknown. As we move forward in the search for extraterrestrial life, we must also grapple with the ethical dilemmas that come with this pursuit. What happens if we find life? Should we attempt to make contact? Or is it safer to observe from a distance? Could our interactions with extraterrestrial life harm it in some way? Or could it harm us? These questions are no longer theoretical. They are becoming practical concerns as we approach the possibility of discovering life on other planets and moons. One of the primary concerns is contamination. If we find microbial life on Mars or Europa, how do we ensure that we don't unintentionally contaminate these environments with Earth-based microbes? Conversely, how do we protect Earth from potential biological contamination if we bring samples back from other planets? NASA and other space agencies have developed strict protocols for planetary protection, but as exploration becomes more ambitious, these protocols will need to evolve. There's also the question of whether we have a moral obligation to protect alien life if we find it. If we discover life on another planet, should we preserve its environment, even if it prevents us from exploring or colonizing that world? Some ethicists argue that alien life, even in its simplest form, has intrinsic value and should be protected from harm. Others argue that humanity's survival and expansion into space should take precedence. But the search for alien life isn't just about finding microbes or signals from distant civilizations. It's about understanding the universe and our place within it. It's about expanding the boundaries of knowledge, pushing the limits of technology, and confronting the unknown with curiosity and wonder. Moving forward, humanity stands at the threshold of discovery. Whether we find life next year, next decade, or next century, one thing is certain: the search for extraterrestrial life will forever change how we see the cosmos and ourselves.